here's kind of where we're at, everybody. What we're learning today is we are going to complete our chemistry triangle and coming back to the what do you see side. So we started the unit by doing all those various demos, right? And you just kind of guessed what was going on at the molecular level. We then talked about the molecular level in terms of IMFs and polarity, how to write them symbolically. Now we're going to bring it back. Today is the day where we will answer how all those demos we saw actually work and what's going on at the molecular level. Once again, connecting it back to it's all due to intermolecular forces, okay? The plan today is we'll do notes for probably only about 15 or so minutes. We don't have very much left. After our notes, then we just have a practice assignment to kind of where you'll work with a group and kind of talk about some of those demos and what happened and come up with an explanation. And that's it for this unit. So your homework assignment for tonight, we should be able to finish technically this one in class. You'll just upload it and then to take the Unit 6 test online over the weekend. I am going to leave it open through next Wednesday, so you can kind of pick accordingly when you want to take it. But that is your homework by then. Okay? Instructions are online. It's very similar to all last term, which is through Mastery Connect. It's only 20 questions total, so it's not a super long test. But yeah, Rachel.
Will the test be uploaded tonight or tomorrow?
It's already there.
It's already, and it's like ready for us.
It's ready to go. Yep. Okay. So if after school today you're ready, you can take it.
Okay.
Yep. Great question. Okay. Any other questions on that? Just a reminder, obviously because it's been a while with Christmas break, you can make a note card, right? 3x5, right on both sides for the test. You can use a calculator. Obviously, definitely have a periodic table handy. Because of polarity and stuff, you're going to want one of those. But any questions about that? Okay, let's jump in to the application side here. Okay, so we've learned that IMFs are the reason why molecules stick together. Hence the reason why I made it analogous to the friendship force. Right? It's the force that holds them together. Two separate things though, right? It's not a bond within, it's a force between. Okay? Because of this force, these are some of the things we see in our life that are a result of them. Number one, it increases the melting and the boiling points of a substance. Now, why at the molecular level would something with high intermolecular forces have a high boiling point? Yeah, Jared.
Because they want to stick together more, so they're not as easily to be separated.
Yeah, because boiling means we're going to pull them apart, right? So something has really high intermolecular forces like water, because it has hydrogen bonding, those little water molecules want to stick together. They're really good friends. And so it takes a lot of energy to get them to pull apart. It's a very simple thing, but I don't know if you've appreciated the fact that water has hydrogen bonding. Okay? If water didn't have hydrogen bonding, it sounds weird, but like we'd all be dead. Because its hydrogen bonding causes all these things in our life to happen. For example, a high boiling point. Why is it good that water takes so much heat to boil?
Purified.
True, to clean it. Other reasons, why would it be bad if water boiled at like 50 degrees? Michaela?
Probably burn ourselves.
Ooh, not a bad thought, but interesting. So boiling actually has nothing to do with temperature, it's just the phase change. So if water boiled at 50 degrees, the water would actually be cold, but it'd be boiling. It's actually very similar to what we saw on the second day with the dry ice, right? Dry ice, in a sense, is boiling away, but it's freezing because it's just the phase change of it. But I'm glad you brought that up. Have a smiley face for that. Ben?
Would we be boiling?
Yeah, number one, we have water inside of us, and our body temperature is 98 degrees. So that sounds extremely painful.
We'll be boiling.
Right? I mean, think of our puddles outside, or our lakes and our oceans, right? If water boiled really easily, it wouldn't be there anymore, right? We'd be a dry planet, which means we wouldn't survive. So, very good. Then have a smiley face. I didn't say that already. Okay, another thing it increases is this force of cohesion. If you haven't learned about the definition of cohesion, there it is. Sometimes you talk about it in biology. But literally it's what IMFs are, but it's the sticking together of particles of the same substance. A cohesive force. So the stronger IMF, the stronger that force is of them sticking together. Okay, it increases the surface tension of the molecules. Surface tension, let me bring up a picture here, is the attractive force between particles in a liquid that minimizes surface area. Okay, so, I did this little demo for you. It kind of has obviously a little magic trick behind it. Oh, that didn't work as well. Okay, here we go. Let's see if this will work again. I kind of messed up my jar a little bit. Okay, there you go.
Oh, I've been that before.
She's just a water bender, you know?
Yeah.
Okay, so, Shannon, say that again.
Surface tension.
Yeah, so this is working through a process of surface tension where the water molecules are linking to each other. Now, once again, it's kind of a magic trick for those that are farther away. Because it's not as cool as maybe as it seems, where it's like, looks like it's defying gravity. I have glued a window screen to the top of my jar. So there are holes in it, but it shows you that literally the little water molecule surface tension is strong enough to kind of grab to each other and grab onto the wire and not fall through, right? The good question that I'm always wondering is, what would be the biggest size hole you could make and it still work? Because it will get to a point, these forces aren't the strongest, right, where gravity would overcome it and it would fall through. Or, like, I've always wondered what size of jar could I use? Like, could I do this like with a bucket over a student's head and they wouldn't get wet? Or would the bucket have too much water and be too heavy, right? I don't know. I've never tried it before. So.
You should try it on me.
You volunteered? Anyone okay to take a shower this morning? But that's the idea of surface tension, right? It's the same reason why water beads up on a surface, right? Why water forms little spheres. Is because those little water molecules are linking to each other, and the sphere is the smallest way to do that. So, okay, another thing that we see is this idea of that polar substances obviously stick to other polar things, right? The dipole to dipole force. And so this helps in capillary reaction, where capillary reaction is the attractive force between the surface of a liquid and the surface of a solid. In our demos that we did, this is how, I'll see if I can find it or if the other teacher still has it. The little glass thing I brought around that had a bunch of different tubes, right? And the farthest tube was farthest up. This was working through capillary action. It's actually the same thing as next time, well, if you use straws anymore, but next time you have a plastic straw, okay, if you stick the straw in water, you should notice that the water level in the straw is higher than the water in the cup, right? This is working through capillary action, where the little water molecules are climbing up the sides of the straw to a certain extent. Now, they only can climb so high, once again, because of gravity, right? It doesn't overcome everything, but they can climb up. Now, the smaller the tube, the higher they can climb, right? That's why literally, like in hospitals, they have these things, they're called capillary tubes. They're very, very, very thin glass straws. Very, very thin. They're so thin that you can touch it to so you prick someone's finger, get the blood, right? And then you touch a capillary tube to it, and it literally looks like the tube just sucks it up. But in a sense, there's no sucking going on here. It's just the little molecules are climbing up the walls inside. Okay? Has anyone seen a capillary tube or had it used on them before? I don't know how much they use them anymore, but yeah, there's something sticky on that jar, and that's all. Something in the seat. Okay, another thing that we see because of these intermolecular forces are mutual solubility. Now, solubility, just as a reminder, means dissolving. Okay? So the reason why something dissolves or the reason why something doesn't dissolve is all due to the fact of its intermolecular forces. Okay? Or in a similar note, miscibility is the ability to mix. So two substances that won't mix with each other have opposite forces. We have kind of this catchphrase in chemistry where we say like dissolves like. So polar substances will dissolve other polar substances. Non-polar substances will dissolve other non-polar substances. But if you get polar with non-polar, they don't mix. Right? Like dissolves like because they're attracted to each other. So with that, let's think about the food coloring and oil and water demonstration that we talked about. Okay, so this is the one, right, where we had the tube, we had oil at the top, we had water at the bottom, and I dropped in a drop of food coloring. Remind us, what did we see happen with the food coloring?
It just stayed at the bottom of the oil.
Good, so it stayed as a little ball inside the oil. In a sense, did it mix with the oil? No. So what does that tell you about the forces of the food coloring? They're opposite, right? Whatever oil is, it must be the opposite. What did it do when I finally got it to break through? Then it dispersed. So what does that tell you about its forces with water? That they must be similar to each other, right? They like each other, right? Friendship force unites. Okay? We'll talk more about that one as we keep going. Any questions so far about any of these kind of terms, definition-wise? Okay, I'm going to show you a comic. I think it's on the bottom of your page. But it's a good sign that you're understanding what I'm talking about if this is a little funny to you. If you don't get it, then we might need to define some words again.
Save my man. Save him.
He's dissolving.
He's dissolving, guys. Stop laughing at him.
It's funny.
Save him.
So why is he dissolving?
Global warming.
Polar bear. He's a polar bear. And what's water? Is water polar? Water is also polar, right? So like dissolves like. But he's not a polar bear, so thanks for the pity laughs at my chemistry joke. Okay, let's try a practice problem that's similar to some things you might actually see on the test about this application side. Okay? So question number 1 says to put the substances in order from lowest to highest boiling point. So first off, let's review our connection. What was the connection between IMFs and boiling point? Something with high IMFs means what?
High boiling point.
Very good. Equals high boiling point. So indirectly, what this question is saying is it's saying put the substances in order from lowest to highest IMFs. So our first question is, well, we got to decide what IMFs these have. Okay? Do they have London? Always, right? So I'm just going to make a little note under here. So this one has London. This one has London. This one has London. Say it again, Jared. Oh, okay. Okay, second question, do they have dipole forces? Okay, come to this first one, nod your head yes or no. Does it have a dipole?
No.
Good, no dipole. Does it have hydrogen bonding? Nope, so it's just London. Okay, come into this one, nod your head yes or no. Does it have a dipole? Definitely, because one side, right, all of them are going to be drawn that way. Yes or no, does it have hydrogen bonding? No hydrogen. Okay, coming over here, does this have a dipole force? Yes. Once again, symmetry of it, right? It's not symmetrical on all sides. In this case, they're all going to be drawn towards the oxygen. Does it have hydrogen bonding?
Yes.
Yes.
Heck yeah. So we're doing?
So like so far, at least the ones that I'm remembering you looking at,
Yeah.
like whenever there's hydrogen bonding, it's also polar. So is that always the case, or?
It's hard for me to say always because there's a lot of chemicals in the world and I don't know all of them off the top of my head. But I can't
Why not?
think of a case where you would have hydrogen bonding without it being polar.
Okay.
Why not? Why don't you know all of them?
I know.
What
I know.
What did I
Slacking.
sign up for?
You're gonna have to be-
That's what I said. I'm getting, I'm there's so many chemicals in the world, so good connection. Okay, so if I want to put them order from lowest to highest boiling point, they're actually already in order,
Heck yeah.
right? Because the more forces something has, the higher the boiling point's going to be. So this would be the weakest. It's going to be less than this. It's going to be less than.
The these things. Oh,
Okay.
what does IMF stand for, like,
Oh,
technically?
intermolecular force.
That makes sense. Okay.
Just our abbreviation for that long word. Okay, with your table buddy, I want you to try to answer question number 2. Ready, set, go. Set your pencil down when you're done.
Carbon and hydrogen. Carbon, hydrogen, chlorine. Hydrogen, carbon, oxygen,
Okay, write down your answer for number 2. Put them in order.
So if we label
So
this one as
more
situation 1,
IMF
this one is situation 2.
Stronger.
This has a more
But it's backwards.
hydrogen bonding with the
More
order. With the order goes
Oh,
three.
adhesion does like it also is part of it too. Yeah, it's actually pretty similar in definition to like what we talk about with capillary reaction, because adhesion, right, is like 2 different substances. Yeah, I just didn't bring it up, but it's due to the same property. So yeah, no, good connection. Okay, everybody ready? If you have this order, you can have a smiley face.
I don't even know how to tell, man.
Okay, so the connection here is, right, surface tension is how things stick together. So, for IMFs, the more things stick together, well, that is not up there, the greater the surface tension. Okay, this is why, once again, it hurts to belly flop into a swimming pool. Is because water has pretty strong intermolecular forces. So it has a pretty strong surface tension, right? Once again, the little water molecules are playing like a game of Red Rover against you. Right? When you jump in, you can literally feel that surface tension. Now, how many of you have ever been up to Park City and watched the ski jumpers jump into the swimming pools before? Anyone seen that? It's so cool. Only 2 of you? A few of you? It's really cool. If you, hopefully, once you know life is not a pandemic anymore, you can go watch it. But pretty much you can go and they like do these tricks into a giant swimming pool. What do they do for those that have seen it to the swimming pool though? Do you remember?
Don't they like shake it or something?
They have jets at the bottom.
Yeah.
So they blow these jets from the bottom to do what?
To keep
Oh,
the water
keep the
moving.
surface tension.
Yeah, to keep the water moving and break the surface tension. That means that if the person lands a weird way, it doesn't hurt. They could literally belly flop into the pool with the jets and wouldn't hurt. I know, me too.
Dream job. Let's go.
Here's another thing I want to try. Is could we get something besides water and belly flop into it and it wouldn't hurt as much because
Oh yeah, belly flop into milk.
like fill up a swimming pool with like oil?
No, you cover yourself in
Oh what? I don't want to do that.
Ooh, that's an interesting thought too, Connor. Yeah, Carter.
What would it feel like?
What, to jump into oil?
Well, no, it's like belly
To
flop
not.
without any surface tension.
It tastes real bad.
Jumping in the rest of the pool.
Yeah, like,
normally.
yeah, because you would just
I-
go
I
through
always
it,
feel
right?
like-
I guess it would feel like getting hit by a wave at the beach.
It's just
I mean, it's kind of like this, it's a similar idea of how like gymnasts and stuff use like foam pits for tricks. The idea of a foam pit is they can do whatever trick they want, and if they don't land it right, it should prevent them from getting hurt, right? Because, so I don't know, like, because you would just like fall through, like falling into a pillow. I don't know, that's a good question. It'd be fun even just to jump into a normal, like not like with a bunch of jets. We'll have to find out. Hey, can we come jump in your swimming pool? It's
I
for
wonder
science.
if that make like divers like happy too.
Yeah, I'm pretty sure a lot of like professional divers, they do a similar thing too. Like when they're practicing new tricks.
Oh, I was gonna say, like,
Yep, they have jets in the pool. So I know. Do you guys know? Because BYU has a diving pool, and I'm pretty sure their diving pool has jets. Do you guys know?
I don't know.
I'm not sure. So at least the old pool. I don't know because when I was in high school and swam, the diving pool is right next to the state pool. I'm pretty sure I saw that, but yeah. Any other questions on that? Okay. Oh yeah, Tanner.
So like, you know when you're at the beach and you get hit by like a pretty decent sized wave? Would it kind of be like that? Because if waves are moving, then they don't have
Ooh.
surface
It's
tension.
because you'd still feel the
You
force,
still feel
but
the
it
force
doesn't
in it,
like
but it's like, it
hurt,
doesn't,
like
slap
it
you.
doesn't slap you.
Yeah.
Maybe.
Would it be like that?
Yeah, because you're still hitting something, right? You're not like hitting air.
Yeah.
That's a good analogy. I don't know for sure, but I say that's logical. Because yeah, 'cause waves don't have surface tension, right?
Yeah.
Yeah, that's a good thought. Okay, let's look at the bottom one here, everybody. Okay. This one says identify for each of the above substances if they would dissolve better. We're looking at dissolving in water or carbon tetrachloride. Okay. I'll remind you, carbon tetra. What does tetra mean again?
Four.
So this is CCl4. Okay, we know water, obviously. Okay, so if I'm looking for dissolving, what helps things dissolve in each other?
Like substances.
Similar forces. Okay, so we're looking for like, so we already know the forces of these. So let's figure out the forces of the thing we're going to dissolve in and see what lines up best. Now, obviously, we know they both have London, because everything does. Okay, so make yourself a little note here. Okay, we know water has what forces? Dipole and hydrogen bonding. Is this going to have any other forces besides London? No, it doesn't. It's just, I can draw it for you. It's just a perfect tetrahedral that's perfectly balanced.
Ooh.
Okay, so for this guy up here, CH4, which two would he dissolve better in?
The carbon tetrachloride,
Why?
because they're almost identical.
They both only have London forces, right?
Yes.
Okay. All right, middle one here. Which one do you think it would dissolve better in?
Water.
Yep, it's going to dissolve better in the water. CH3F. Because those dipole forces can overlap and attract to each other. Okay, finally the last one is obviously going to dissolve best in water. Questions on any of these questions? Yeah, Jared.
So when you're talking about dissolving, you talked about polar versus non-polar and
Yeah.
how they don't like dissolve in each other.
Yeah.
But does hydrogen bonding have any like say in that? Like if you have water, but then you have another substance that has dipole or whatever, would something like would that make a difference or?
It would still dissolve, like, so both of those would dissolve in water. The one with hydrogen bonding we could predict would dissolve even better.
Okay.
Yeah, because the hydrogen bonding would help even more. So, yeah, it doesn't like stop it from dissolving, but it could help it dissolve even more. So, good question. Any other questions? Okay, go to your assignment packet for me and pull out the last worksheet you haven't done that says INF applications. do this one slightly out of order because I want to have some discussions with our table buddies. The front page has a lot of just reviewing the definitions we talked about. So flip to the back side for me, everybody.
I don't like definitions anyway. So,
Yeah. We'll come back to them later though.
dang.
You might have to like them later. Okay, what I want you to do is with your, I'm going to put you into a group of 3 to 4 people. Okay, and I want you, can I just let Josh, so everyone's on the right spot. So we're looking at this chart right here. Okay, with your group that I put you in is I want you guys to have a discussion together to answer coming back to those demonstrations we saw at the start of class, right? Where you're explaining now based on what we know about intermolecular forces. Okay, once you have these done, raise your hand and one of us will come look and just make sure we're on the right track, and then you can continue on with the rest of the worksheet. Okay, any questions? Okay, so let's do, we can do a group of 5 here. You 5 kind of all discuss together. Okay, so here's how I want you to do it, is figure out who is the oldest in the group. Okay, the oldest person will start with demo number 1 and give their thoughts on why they think it is. Once again, don't be afraid to fail because we fail until we don't. Okay, you learn a lot more from saying wrong things than from staying silent. Okay, then you can discuss as a group, then go to the next oldest person in the group and they'll talk about the next demo. So I kind of want to have a different person lead off on each demonstration. That way everyone has a chance to kind of share their thoughts. Okay, you guys be a group of 5. We'll do,
Can you get
Melody, do you want to come up here for just a sec and you guys can be a group of 4? And then you guys can be a group of 4.
Please go over.
Well, I'm sorry, I'll just go right over there.
Let's,
Are you 17? Okay, you get to go first.
Surrounded by children.
Oh, wow.
you guys
I'm very 17 with like a horse.
How old are you? 17.
let's do,
Ah.
Because I'm 16.
yes, you two
Okay.
rounds, you guys be a 4, and then you guys.
Okay, rubber band on.
Got it? Okay, ready, set, go.